so much, Nicholas, for the introduction. So I don't know, I have to start or just a little bit explain about the background?
No, go ahead. I think you can
Okay.
start.
Okay, thank you. Okay, as you mentioned, the topic that I'm going to talk about is about uncertainty quantification and calibration of imitation learning policy in autonomous driving. So currently I'm working in Agents and Simulated Reality Group in DFKI, or German Research Center for Artificial Intelligence. And my advisor, who is familiar for you, is Dr. Christian Müller. And I'm also having my supervisor, who is Professor Susalek, who's leading the Agents and Simulated Reality Group. Okay, let's get started and see. So here you could see an outline of this talk. So I will briefly introduce Bayesian deep learning to better understand the context of the work. And then I will mention and enumerate some of the motivations behind this talk so that we can see why we are actually estimating or quantifying uncertainty and what we can do with this uncertainty in several applications. And I will briefly introduce my recent work, and we will see that in that work, we will quantify different types of, sorry?
No, it's just somebody's got a mic open.
Okay, I'm confused. I thought that it's a question. Okay. And I will show you the architecture behind this work and some evaluation metrics and experiment, and eventually some future directions. And so let's start with the fact or definition about what is the Bayesian deep learning. So you better probably it would better to probably start with the classical neural network. So in classical neural network, we usually estimate a fixed set of parameters using maximum likelihood estimate in order to form the predictive distribution. Here, the x is the input and y is the output, and theta is the fixed set of weights calculated based on maximum likelihood estimate. So here we use optimization in order to find the best setup of our parameters for the neural network. So it's only a single fixed set of parameters. But in contrast, in Bayesian deep learning, we define a distribution over weights given data so that we can sample from this distribution. And the predictive distribution, as you could see, is a little bit different from the predictive distribution that we had in classical neural network. And here we are actually using marginalization, which means instead of having a single parameter, we have a distribution of parameters so that we can sample from that and average over all setups of our weights. So it has several benefits, and probably the most important benefit is that it allows us to calculate or quantify different types of uncertainty, especially in safety critical tasks such as autonomous driving. And there are two kinds of uncertainties. And first is called epistemic or model uncertainty, which capture the uncertainty over network parameters, and it shows how much the model doesn't know about for example, the given inputs, because we have sometimes a limited data set and we have to train on that limited data set, and the model might not know about the other regions of the data set. And you could see that we have high epistemic uncertainty usually for novel objects. For example, here we have an object detector. You could see that it exposed high epistemic uncertainty for a helicopter in an urban environment, because usually these models are trained on road with vehicles and pedestrian and other things, and these novel objects might expose high uncertainty for the model. On the other hand, we have aleatoric uncertainty, which represents the uncertainty in observation, and it actually captures the inherent noise that we have in output. And you could see that, for example, again, in an object detector, you could see the occluded objects or objects for which we have inaccurate labelings in our data set might expose high aleatoric uncertainty. And the other benefit of using Bayesian deep learning is probably the fact that it can detect out of distribution detections or samples. And this is a major problem, especially in autonomous driving. As you could see, we have a long-term distribution of scenarios, or we have lots of critical scenarios in autonomous driving, like the image that you could see. The vehicle suddenly sees a completely novel object. And in these cases, the typical neural networks are usually overconfident and might predict dangerous actions, which is not good in safety critical tasks. But instead, in Bayesian neural network, we can detect these out of distribution scenarios or samples with high model uncertainty. So it gives us a handle for detecting these scenarios, and then based on this detection, we can, for example, in some ways act cautiously. It also has other benefits in safety and robustness. Here you could see two different pipelines based on deep learning and Bayesian deep learning in autonomous driving. You could see we have input, perception, prediction, decision, the usual categories of tasks that we have in autonomous driving. And you could see that in each category, we define some low-level computer vision or prediction tasks, like, for example, object detection, lane detection, things like that, and prediction, past prediction. And if we use deep learning for each of these subtasks, we have hard decisions. But in contrast, in Bayesian deep learning, we have some confidence interval or boundaries that can be propagated towards the whole pipeline, so that the failure that might happen in one module can be also propagated to other module, and other module might adjust themselves based on this uncertainty. So we will eventually have safer actions based on this paradigm. And it also provides us some kind of interpretability or explainability. For example, this is an example of work that you could see that in semantic segmentation and depth predictions, which are two popular tasks in autonomous driving, you could see that the uncertainty shows here in the class boundaries, or for distant object or for unfamiliar object here in this picture, you could see we have high uncertainty. And this can, for example, show some kind of model ignorance. And it's really important to see in which areas or for which objects the model doesn't know that much. And you could see, for example, for reflective area or transparent areas, you could see we have, again, high uncertainty, meaning that the model is not really sure how to deal with this, for example, glasses or mirrors and things like that. Okay, so now let me briefly explain my recent work, which is uncertainty quantification and calibration of imitation learning policy in autonomous driving. So the main idea behind this work is to combine the Bayesian deep learning with imitation learning to provide uncertainty for actions. And I'm motivated by the fact that current state-of-the-art imitation learning policy in autonomous driving usually do not consider the uncertainty in actions. They just only care about performance. So they might fail completely for out of distribution scenarios, although they have a good performance on the predefined data set, but it doesn't mean that they would have a good performance on real world, because the real world might include many uncertain regions and uncertain scenarios. So for this, I extended a state-of-the-art imitation learning policy with 3 common uncertainty estimation methods. So you could see MC dropout, deep ensembles, and the aleatoric uncertainty. And since, as I mentioned, the neural network can produce highly overconfident predictions, I also adapted a recalibration module on top of our policies in order to make the uncertainties more calibrated. And eventually I did experiments regarding driving performance and the quality of uncertainty. So here I give you a brief definition about the types of uncertainty. So you saw the predictive distribution. Inside the predictive distribution, we have this probability or distribution over weights. The question is that how we can calculate this distribution. And for this, we can use, for example, Bayesian inference by defining a likelihood. And for regression, usually we define a Gaussian likelihood by, as you could see, the mean of the Gaussian can be predicted by the neural network, and we can have a fixed, for example, standard deviation. And because we have lots of weights in neural network, the exact inference is not possible. So we have to rely on approximation methods. So, and we can approximate, for example, this distribution using a tractable distribution Q parameterized by W. And then the predictive distribution can be approximated by taking a few samples from that tractable distribution and forming the T Monte Carlo samples. And in this case, for example, in regression, we have a mixture of Gaussian because we define the likelihood as a Gaussian. We can further simplify this mixture of Gaussian with a single Gaussian, for example, by calculating the sample mean and the sample variance. And this sample variance is called epistemic uncertainty because it depends on the network weights. If we have the same weights for all theta hat I, we would have zero uncertainty. And here we can also let the network to predict both parameters of the likelihood, both mean and standard deviation or variance here. So this variance is called aleatoric uncertainty. And regarding the calibration, I should also note that a model is said to be calibrated if the probability that it produces matches the probability of the true probability of that event. Let's give you an example. Here you could see an object detector again. We have 90% confidence for all of these samples. So we have gathered these samples, all with 90% confidence. And you could see that we have two false positives in the end. But the model is calibrated for 90% confidence because 90% of the predictions are correct. And this is the empirical probability or true probability. So we can say that this is a calibrated pedestrian detector because in 90% it produced correct answers. So regarding imitation learning, before going to the imitation learning, I have to explain briefly two methods for estimating uncertainty. The first one, which is a popular method, is MC dropout, which estimates epistemic uncertainty, and it's based on the variational inference. And the fact is that we apply dropout on every weight layer, and we keep them activated during test so that we can have stochastic output of this of the neural network. And it can be represented or interpreted as the variational inference. So you could see in the paper that they have this proof that this could be a version of variational inference. So to summarize, you could predict the epistemic uncertainty from this MC dropout methods. And we have also deep ensembles which can predict both of uncertainties. And the fact is that we have an ensemble of models with theta 1 to theta t, which are actually trained based on maximum likelihood estimate. And each model produces the parameters of the Gaussian, mean and variance. And once we have this parameter, we can form the the final variance, which is the combination of aleatoric and epistemic uncertainty. And regarding the imitation learning policy, the state-of-the-art policy that we use is called CILRS. And so this is a variant of imitation learning policy. And to be more precise, it's a behavior cloning policy. And it means that we have a bunch of state action pairs from the expert demonstrator. And we use supervised learning over these state action pairs to minimize a loss function, which is the distance between, or it could be any loss function distance between the predicted action and the action produced by the expert. The expected loss over the state distribution induced by the expert. So here in this work, we gather RGB images together with some sensory information like the speed, and we train using supervised learning to predict some actions. And the policy is also conditioned on the navigational commands, because we have to know, for example, if we are approaching an intersection, the policy should predict, for example, if we want to go left, the policy should be somehow branched into different navigational commands. So you could see better in the next slide. So here is their main architecture. You could see that this is our aleatoric agent, and the other agent can be somehow explained better based on this aleatoric agent. As you could see in the bottom, we have the Carla simulator, and we use the image, front-facing camera image, together with speed of the vehicle, and we extract some features from them. And you could see in the conditional module, we condition based on the navigational commands. And we have, for example, here 4 navigational commands. But our contribution here is that we somehow modified this, that the conditional module produces the so we modeled each control command as an independent Gaussian distribution, and we predict the parameters of that Gaussian. And once we have these predictions, we pass this prediction to the calibration module, and the calibration module calibrates the predicted uncertainty based on the true or empirical uncertainty. And there is a feedback loop that we will pass this information back to the agent. So for MC dropout agent, it follows the main architecture, except that here we are not calculating the aleatoric uncertainty. It's all about epistemic uncertainty. So we don't have that blocks in green, if you notice. And so the other fact is that we use the last layer dropout. We keep them activated during inference, and we sample five times during test. And we calculate the sample mean of these predictions, and then this information will be passed to the calibration module. And in ensemble agent, we have an ensemble of 5 networks corresponding to the 5 samples in the MC dropout agent. And here we train each of them independently to predict the Gaussian distribution or the parameters. And then we use the sample mean and sample variance to summarize the stochastic output of these parameters. And for calibration module, we use isotonic regression, which is an existing calibration method in regression task. And to build this isotonic regression, we need to build a recalibration data set for each control command independently. So you could see we have 3 control commands, and for each, we calculate some predicted CDF or cumulative distribution function and their corresponding empirical CDF. So we have the predicted and we have the empirical, and we learn a regression model that given this predicted CDF, it maps them to the empirical CDF during the inference, so that we can have calibrated uncertainties during the inference. And regarding the evaluation metrics, we evaluate the agents from two perspectives. One is the driving performance, so in which we use Carla simulator, and there is a no crash benchmark in this simulator. And in this benchmark, we have, for example, 2 towns and 6 different weather conditions. The first town is only used for training, and we test on the second town, and there are 4 weather conditions during test and 2 for 4 for training and 2 for test. And there are also 3 tasks: empty town, regular and dense traffic with 0, moderate, and a large number of pedestrian and vehicles inside each town. And we have to, for each task, we have to complete 25 episodes, meaning that starting from some position in the city, going to a different position. And we calculate the number of successful episode, which is defined as reaching the goal within the time limit and without the collision, and we count the number of these successful episodes. But regarding the uncertainty, we also evaluate their quality in terms of calibration plots and expected calibration methods. So here you could see intuitive examples before going to the main problem. You could see that in this toy regression problem, we define this toy problem that represent our actual problem. Here we have 3 models: aleatoric, MC dropout, and ensemble, representing our 3 agents in the actual task. And here we have to regress this. This is the training data. You could see we have an input dependent noise, which we expect that the aleatoric uncertainty should capture. And you could see that the test is also including some regions which are missing in the training data set. And you could see here in these predictions, the blue line is the actual prediction for the network. The red area is 90% confidence interval, and the black line is the actual data. And you could see, for example, an aleatoric model, you could see we have detected the region for the noisy data as a high uncertainty. You could see that the red area there around the noisy data. So it can, as we expect, it can detect the noisy or inherent noise in the data, but it fails to detect the uncertainty that we have in these regions, which are out of the distribution. And you could see the prediction is quite confident, or let's say overconfident, because it has predicted something with a high confidence. You could see there is no confidence region or wide confidence region, meaning that it's overconfident during on these regions. But on the other hand, you could see on both ensemble and MC dropout, it presents, they present this highly uncertain regions with a wider 90% confidence interval. So you could see when we apply the isotonic regression to make them more calibrated, what happens is that it tends to make this calibration, confidence areas much wider. So you could see that it produces here much wider regions, so it can covers more data point and therefore better calibration. So you could see that the amounts of coverage here to 50% here is 10% higher. And you could see that in this case, we have almost, in these 2 cases, for example, especially here, we have almost a calibrated model by widening the uncertainty over these regions. And you could see that it also represents the effect also clear on the calibration plot. We can see that before calibration, we have highly conservative uncertainties. So as an additional note, consider that the perfect calibrated model represents the identical line, the x equals y line. So you could see, You could see that this is the perfect calibration, but we have highly overconfident models here because the empirical is less than the actual the predicted one for these models. But you could see that after the calibration, they are somehow more calibrated and fit the perfect calibration. So regarding driving performance, we could see that our models perform better than the baseline in the dense task, which includes more pedestrian and vehicles. And surprisingly, with a huge gap from the baseline, you could see that ensemble agent significantly improves the performance of driving in all tasks almost. And this is probably, not probably, could be, there could be one other reason that if we say that we have an ensemble of models, and these ensembles are trained on a subset of data, which each has a number of scenarios, we can better have a model to vote for critical scenarios. And then along with the uncertainty quantification, it can produce better performance. And regarding the quality of uncertainty, we can see that before calibration, the aleatoric and ensemble agents both have conservative uncertainties. And you could see for MC dropout, we have overconfident uncertainties for control commands. And after calibration, we can see that they are almost calibrated, but the fact is that the MC dropout agent is not that much calibrated compared to aleatoric and ensemble, and it shows that the aleatoric uncertainty has a huge effect on making the models more calibrated, because in MC dropout we only estimate epistemic uncertainty, but in both ensemble and aleatoric we calculate this aleatoric uncertainty. Because we don't have this here, probably the network can't make the recalibration module can make it more calibrated, because the uncertainty from the aleatoric type is missing and it fails to perfectly calibrate it, the model. And here you could see the corresponding values for ECEs, or expected calibration methods, of the above figures. So you could see that before calibration, in average, overall control commands, we have better calibration for MC dropout method, and after calibration, after including calibration module, the ensemble method would have the best performance. And to see how the uncertainty behaves in different situations, here you could see that we have visualized front-facing camera images at the moment that we have high uncertainty of both types. For example, these are the samples from top aleatoric uncertainties, and these are the samples for top epistemic uncertainties, sorted from the high to low. And the interesting fact is that in both types of uncertainty, we can see that when the agent is at intersection or approaching an intersection, we have high uncertainty of both types. And this is interesting because for the aleatoric uncertainty, usually we have some kind of noisy labels during the period that the agent is at intersection, because we have different modes at intersections, going right, left, forward, and these could be interpreted from the network perspective as some kind of noisy labels, because given a similar images, we can have different labels, and it could be confusing for the network. And as you could see, it produces high uncertainty in these regions. And regarding epistemic uncertainty, the fact is that I checked these regions in our data set, and it turned out that we have a relatively small portion of intersection in our data set, because the agent is usually going straight along the road. And so we have relatively small number of samples in which the agent is at intersection. So it means that the model really doesn't know, or it hasn't learned enough to handle these situations or regions. And interestingly, it produces high uncertainty for these regions. And you could also see the effect of calibration, what happens after the calibration in these regions. You could see that here in this example, the shaded green area represents uncertainty, 90% confidence interval, and the dashed red line is the prediction, and the blue line is the ground truth. So you could see that we have a wider confidence interval before calibration, but after calibration, it makes it much narrower. And in other words, it makes it more useful, because if the network be free without any recalibration module, it tends to produce wide or conservative uncertainties, because the lack of, for example, enough data, or as I said, multimodality in these areas, it's so conservative, and it produces always a high value of uncertainty, which is not that much useful in our application. But you could see that after calibration, it tends to make it more narrower and therefore useful, so that we can know that this is a valuable uncertainty, because otherwise the values might be high for all regions, including these regions, and we can't really detect critical regions or scenarios or samples. Okay, to conclude this, we estimated different types of uncertainty in imitation learning policy, and we developed 3 agents based on 3 methods of aleatoric MC dropout and deep ensembles, and we compared them with driving performance, regarding driving performance and the quality of uncertainty. And we saw that the recalibration actually improves the quality of uncertainty. And we also outperformed one of the state-of-the-art methods in imitation learning in driving performance. Meanwhile, we are also producing uncertainties. And so it's not about the driving performance alone, but we also can say something about its uncertainty. And we saw that in some regions like intersection, we have high uncertainty, and probably this can help us to design agents in a way to handle these situations better. Yeah, that's it. Thank you.
Okay, thank you, Farzad.
You're welcome.
So nice presentation.
Thank you.
So we are ready for the discussion, and let me see if they have some questions from the audience. Okay, so it doesn't seem to be the case. I can start with asking some of the question. I mean, about the scenario that you have simulated, how complex are these scenarios? I mean, in the different examples that you have addressed.
Mm-hmm. to be honest, we're not defining scenarios like the scenarios that we could see that, for example, we are working in a project currently that we define some scenarios like we have a street, the car is going, and suddenly the pedestrian is crossing with this speed at this weather, at this angle, at this, and to be precise, every attribute of the scenario is defined in that case. But here we just have so many pedestrians, so many cars, and it's like a city. They have their own destination and they are somehow following their path towards that destination with some kind of human-like behaviors, not that much. So the engine is actually responsible for this. So there is no specific scenario here. We have a city that we have many agents that were actually going, but some attributes can be defined, like the weather. So usually the weathers, the more adverse weathers are used during tests to see the capability of policy to somehow be invariant to some, visual effects like change of lights, weather, things like that. And except from the weather, the density or population, there are also some kind of, let's say, variations that, for example, in few episodes, we have just only scenarios that the car should go astray. So these are some simplest scenarios that the model should satisfy in order to go to other, sophisticated scenarios. And then we have turning scenarios. We have more complex scenarios that, for example, it can go to tunnel, for example, go uphill or something like this. But in this work, we haven't defined them explicitly. We just defined the starting and end position, weather condition, the population, things like that. And these are being generated randomly during the city. So we have random starting and end position, random position of pedestrian, and with random navigation mesh, things like that. So yeah, it's kind of like stochastic way of environment and not a predefined exact script-like scenarios.
Okay. Okay.
Question.
You didn't discuss about maybe the future direction of this work and
Yeah.
the open challenges that you have in mind.
Yeah. I have some, but let me just. Can you see this?
Yeah.
Okay. So one important question or challenge that we have in, especially in reinforcement learning, is something called shift and distribution, or it's kind of like the out of distribution, or let's say we have an environment, the agent is working on that environment quite well, and then the agent is going to other environments or new tasks, and therefore we have a shift of distribution for data. Mm-hmm. And it's really challenging because as I said, the network has been learned on some data or some interactions based on some IID assumptions, and now we are violating the IID assumptions in supervised learning. And the whole idea behind this, for example, benchmarks in supervised learning, is that we assume that we are working in IID assumption, meaning that both test and train have the same identical independent distribution. Identical, it should be identical. But here is different. For example, in reinforcement learning, especially in model-based reinforcement learning, we have a problem of model exploitation. So you could see that, you could see that in model-based reinforcement learning, we first, can you see the pointer?
Yeah.
Good. So we first do some kind of interactions with the real world in order to gather some data, and then we use a supervised method to learn a word model, a model of our world, how dynamics actually work. And the word model or dynamics actually predicts the next state and the reward or cost given the current state and action, meaning that performing such an action at that state, what would be the next state and what would we get from the environment as a reward, or what's the cost of doing this state at this action. And the problem is that during model-based reinforcement learning, the dynamics can be queried with out-of-distribution states or action, meaning that the policy, which actually predicts action, can predict some actions that from the word model perspective, those actions are out of distribution. And the problem is that if you see this, the problem is that we have some, for example, region or distribution of data in which the model, the word model, has been learned or trained. And for the rest of the region, the model really doesn't know how to act or how to predict. And since in model-based reinforcement learning, the policy tries to maximize its reward, it tries to somehow produce some actions. So because since we are maximizing the reward, and the policy learns that producing some actions which are outside of the region in which the model is trained can make or force the model to produce some, states in which we get higher reward wrongly. I mean, the word model can produce high rewards or low cost in this region in a wrong way because it doesn't really know how to do or what to predict in these regions. And since the policy somehow knows these failures in word model, it tries to produce more actions in these regions by knowing the fact that probably the word model doesn't know how to deal with this action and therefore produce high reward values which are quite wrong. And the problem is that the policy is somehow exploiting the model, and it knows that in some regions the model doesn't know anything to do with those predicted actions, because here we are inputting the actions predicted by the policy, and the policy tries to put some actions that the model doesn't know and produce some high rewards because we are maximizing the reward in our policy. And this is a critical problem in reinforcement learning. And it turns out that we can, for example, somehow solve this problem by epistemic uncertainty. For example, one naive solution would be just to have for example, a loss function or a constraint based on the uncertainty of the word model, saying that we should also maximize the reward by considering that we should also minimize the uncertainty of the word model given those actions. And in this case, we have somehow satisfied both requirements. So the policy is not free to, or is not allowed to produce any actions, because it might produce high uncertainty. The word model can produce high uncertainty for those actions, and therefore the loss function would be higher than before. And this is, for example, a simple solution that we can include the uncertainty of the word model into our loss function in order to balance this competition between the word model and the policy. And I think this would be enough. I had two future work, but let's see first if there is any question.
Okay. No, I don't have questions on this. I don't know if there are questions from the audience. Okay. So you have additional points that you wanted also to develop?
Yes.
Yeah.
Yes. Let me also show you, but it's on the same side. Let me show you this. I'm not sure if you can.
I can see the slides, but
Okay, good.
the first slide of the presentation is right.
So this is the presentation view or the slide? I think you could see the slide, yeah?
Yeah. Yeah. Okay. Beyond that, how do you?
Oh, yeah. Okay, great. So this is again something similar to this. So we have, for example, here, this is kind of like a new work that I've started along this direction or that side, that we have a word model, actually, as I explained, that we also calculate the uncertainty. The human is actually interacting with the simulator and produce some data in an offline way. So we have the trajectory for the human. So it consists of state, action, reward, and the next state. So from that trajectory, we can calculate the word model, or having a supervised learning method to calculate this word model. And then we have this agent who is actually interacting with this word model. And as I mentioned, we penalize the agent based on the uncertainty of the word model, and to both include the uncertainty and the reward, maximization of the reward. And then it ends up with some better way to handle this shift of distribution, or let's say out of distribution handling. So it was more or less the same as the previous slide that I showed you. And this is currently what I'm working on. This is the high-level idea of what we can do further with this uncertainty in autonomous driving. Yeah, that's it. That was the final.
I have a quick question.
Yeah.
Yes, please.
First, great presentation, Farzad.
Thank you.
It was a really interesting subject.
Thank you.
My question is about how you would handle, how would you characterize auto-distribution generalization or auto-distribution samples in general? Because in my opinion, there are the auto-distribution samples can arise from different stages of the process, right? It can be either, for example, different weather conditions. Well, that's more of a sensory process out of distribution sample, and it might also arise from, for example, an action decision the out of distribution sample, like the garbage bins that you show in this image. So how would you deal with all of these out of distribution shifts?
Yeah, as I mentioned somewhere in the slides, so typically for OOD, we have different methods. So it's not the only method, but here we can detect somehow with the epistemic uncertainty or model uncertainty, meaning that we have different weights for network, and if they are aligned or they are equal, we have a zero variance for prediction. And this variance can be somehow be a good indicator for out of distribution, meaning that if we have a high variance in these regions, in this, for example, the car is seeing this garbage, you could probably estimate this epistemic uncertainty. It could be an indicator, but we also have some other ways, like, for example, we can have a density estimator and then estimating the density of the training data, which is, for example, based on the human data. And then we can see based on the likelihood of the input, we can calculate the likelihood and see whether, for example, if the network produce a lower likelihood for such a sample or higher likelihood, and we can define some threshold for this. But here it's more or less based on the fact that we have a distribution over weights, and the weights can be quite different in some of these situations. One weight can say, yeah, go straight. One weight can say, no, turn left. And they are not agree on some decisions. And therefore, we calculate this amounts of agreement on this situation. And the more they are disagreed, the more probably critical or out of distribution situation we have.
So the way you see this is that the fact that your weights are distributions, you can see them as proposing different hypotheses of
yes,
either
exactly.
decision or perception.
Exactly, yes.
Okay. However, the thing I have a problem with is that, yes, if you try to minimize your well, if you predict your uncertainty, yes, it will tell you whether the sample is within or out of distribution. But minimizing that uncertainty will not necessarily there's no guarantee that minimizing that uncertainty will yield correct responses with respect to the true labels, let's say.
Yeah, it could have a side effect on this, but the question is that, for example, in reinforcement learning, we kind of want to not to deviate from the regions or the regions that we know that much. So we have to slightly,
Yeah, what I mean, for example, is that, well, and this is kind of a stretch, I'm sorry for bringing this out, but
no,
you train a model to only turn left, like if the training data is only turning left, it won't know how to turn right. So, like,
sorry, I couldn't get this. Can you repeat?
If you, let me give maybe a better example. if you never train your model on the roundabouts and you suddenly introduce them at test data, will you expect the model to know how to handle such a situation?
No, yeah, you're right. You're right. Sometimes it's really difficult to come up with the best actions, but at least here we can detect whether we know how to deal or we don't know, and that's at least a level more than not knowing that we don't know anything. Okay, so I'm not saying that this would definitely make it better, not in this case of reinforcement learning, because in this case it can partially solve the problem, because, for example, something that I also didn't mention here, so when you use the so because we have a distribution, you could use the expected values of that distribution for the actions, for example, instead of doing sampling. And it shows, or you could have pessimistic or optimistic bounds. So there are three, for example, ways that either you use a pessimistic bounds to calculate the values for actions, for example, because we are looking for best actions, as you said. So there are three ways. Either we should say that, okay, so these are the means of the Gaussian or final distribution, which correspond to our final actions. And then we have some uncertainty. Okay, let's add this uncertainty to our actions, which means pessimistic bounds. So we decrease the values. For example, if we are calculating the reward and the reward is 10, but we have high uncertainty, we decrease the reward saying that it's 8. Okay, now the policy is a little bit more conservative to selecting that action. Okay, in this case, we have a trade-off between exploration and exploitation. We have probably here less exploration. Okay, but it's more safer, or it's pessimistic. Or in other case, if we want to have better exploration, we add this. For example, we say no, we have 12 reward. Let's go for that action and see what happens. Okay, and because it's an interactive, it can. But currently, based on some recent work, it's been shown that the expected value would be the best actions that we can perform at these situations.
Yeah, thanks for the response. And I totally agree with the uncertainty reduction. And actually in some, well, in the work I have done with a colleague on variational autoencoders, we actually use this same principle to refine predictions, like reducing uncertainty to refine predictions to mitigate this auto distribution shift.
Yeah, nice.
Yeah.
So we are quite on the same page.
Yes.
Okay,
Great.
that's good. So there are some connections, and you can have continuous interactions after the session. So probably, Farzad, if you want to share some of your publications, and you can add them in the slides.
Yeah, sure.
Okay.
Yeah, sure.
Okay. So unless there are still some other questions that some of you would like to ask, which doesn't seem to be the case, I would like really to thank you for this nice presentation and good interaction. And thanks very much. Okay.
Thank you so much for the opportunity.
Okay. Looking forward to continue this discussion with DFKI.
Yeah, sure.
Okay. So you are at the second, third year or of your PhD, or just starting?
It's the first year, actually.
Okay, so yeah.
Yeah, I joined, I think it was, December last year, I joined DFKI.
Oh.
Yeah.
Okay. You're doing a great job, so good.
Yeah, thank you.
So there's still a couple of people who are online, but I think we ended the session. You have any question from your side?
No?
No, it was a pleasure to learn more about what you are doing right now. I have another question indeed, which is related to, it's not really the subject of your work, but it's more related to the connection. I mean, once you have this estimation of the uncertainty, are you planning also to go until the estimation of a safety figure or metrics based on the modeling of the scenarios that you have simulating in?
You said about the safety metrics that.
Yeah, at the end, I mean, you want to assess safety. I mean, to some extent,
Yeah.
you have different
Yeah.
uncertainty, and but the connection between this objective and what you are really estimating based on your theory is not that clear. I mean, we are not at the same level.
So the thing is that we are actually following some benchmarks, and all papers are reporting based on that benchmarks and comparing their value based on that benchmark. And the benchmark is defined based on so for example, based on the collision and based on some infractions. For example, if we go off-road, if we run a traffic red light, if we so there are some quite detailed, kind of interactions that they have defined, they have weighted them. And so in the end, based on these interactions and collisions and time to a time limit, they decide that whether the episode is complete or not. And everyone is actually reporting the percentage of successfully completed episodes. And that's let's say, a unified way that we can compare with other methods. In other case, if we just say, yeah, we did this, for example, we came up with this metric, it's a little bit hard to compare with other methods because no one is reporting on that. But as you said, you're correct in this project that I'm involved in a new project. We are actually, can you hear me? I can't see you anymore.
The quality is really a little bit degraded, I don't know what's going on, but the connection, but I can hear.
I don't have you. Okay. Anyway, in a new work that I'm involved in, we actually defined this scenarios, as I said, with detailed attributes and also some kind of, metrics that includes the safety. But in this work, we just follow the well-known benchmark. Hello?
Yes, Farzad, we can hear you. I think
Okay.
Mohamed has a kind of problem. Mohamed, can you hear us?
Yeah, now I'm
Yes,
back.
okay,
Yeah.
perfect.
Okay.
Okay.
Yeah, I think the problem was from my side because I was in a Wi-Fi connection, and now I changed it. Sorry for that.
Okay, no problem.
Okay, so I think we ended the discussion. So it was a really great pleasure to have you, and
thank you.
hope to continue this discussion. Other opportunities to continue, having other opportunities to continue this discussion. So
Sure.
thanks a lot, Farzad, and don't hesitate to share your publication if you want to, and
Sure,
keep in touch.
sure. And I really appreciate the opportunity that you provided.
Okay.
Thank you so much.
Thanks a lot. Bye-bye.
Thank you. Have a good day. Bye.
Have a good day. Bye-bye.
Bye. Bye.